A capacitor is a device that has a voltage across it as long as there's some charge on its plates. A resistor is a device that has a voltage across it as long as there's a current flowing through. And as you've learned recently, an inductor is a device that has a voltage as long as there's a rate of change of current. And the voltage is equal to negative L, L here stands for inductance, multiplied by the rate of change of current. But we also know from Faraday's law that induced voltage is equal to negative N times the rate of change of flux. So these two equations have to agree with one another. And if we set them equal, we find that negative L di dt is equal to negative N d phi dt. So if we cancel out the negative signs and multiply both sides of the equation by dt, then we get L di equals N d flux. Integrating on both sides of the equation gives us Li is equal to N phi. So this gives us a way to derive the inductance for all different shape inductors. Inductance should be equal to the number of windings of the inductor multiplied by the flux divided by the current. In other words, if you have a solenoid and no current flows through it, then there'd be no magnetic field in it. And so, well, in this case, it would be 0 divided by 0. So we won't get very far with it. But if the current does flow, then, if current does flow through the solenoid, then there's a nearly uniform magnetic field passing through the solenoid. The stronger the current, the stronger the magnetic field. In fact, there's a direct relationship. As the current in the solenoid increases, then the flux, the induced flux, the self-induced flux of the solenoid also increases. And it increases with a direct proportionality, and that proportionality has to do with the inductance. So this equation might make you think that as current goes up, inductance goes down because the current is in the denominator of the equation. But that's not the case at all. As current goes up, then more and more magnetic field lines would appear in the solenoid. And so the solenoid has created its own flux. So as the current increases, the flux increases proportionally, and the inductance stays the same. As we found in a previous lesson, in fact, the inductance of a solenoid is equal to mu naught times n squared times the area divided by the length. Here we want to find the inductance of a toroid in the same manner. When I say the same manner, I mean we want to start with the statement that inductance should be equal to N phi over I. So let's see. Flux is equal to the integral of magnetic field times area. When magnetic field is constant, and we can take it out of the integral sign, and we can say that flux is just B times the integral of dA, which of course just gives us B times A. So that's the beauty of a toroid. It's a shape that has a uniform magnetic field inside of it. And the thing about the toroid is the magnetic field lines are contained entirely within the toroid, and the magnetic field outside is equal to 0. Okay, so if we're starting with step 1 of our derivation, then we get to step 2, we can replace flux with the product of field and area. Now we have to determine what's the magnetic field in a toroid, and there we get to use Ampere's law. So Ampere's law says, oh, I'm sorry, I just caught a mistake. This shouldn't be a closed loop integral. This should just be integral of B dA. Closed loop integral, that's for Ampere's law. The integral of B ds is equal to mu naught times I enclosed. Okay, so we need to make an Amperian loop for our toroid. Let's see if I can make this stand out. Let's use bright purple here. Oh, there we go. That's my Amperian loop. Okay, well, the magnetic field lines, let's see, I've already drawn them in green. Let me draw them again in orange so they stand out. Oh, so at all points along my path ds, the magnetic field is parallel to my path, so I don't have to worry about the vector nature of this equation. Okay? And the field is the same strength at all points, the magnetic field. That part of my Amperian loop is just as strong as it is there, is just as strong as it is there. So I'm going to take b out of the integral sign, and I'm just left with b times the integral all the way around my loop is equal to mu naught times I enclosed. This gives me b times 2 pi. Here, let's call the radius of our toroid capital R. So we get b times 2 pi r is equal to mu naught. Now, the amount of current enclosed, well, the current passes through my Amperian loop. Let's see the way they've drawn it. Current goes this way, so it comes around and behind. And there we go. Current is flowing that way, then wraps behind, and then flows in again. And the current flows into my Amperian loop as many times as there are windings of the loop. I don't want to bother counting them, so I'll just give it the symbol n. Okay, so it looks like b is equal to mu naught ni over 2 pi r. So there we go. We can make a substitution and get to step 3 of our derivation. The inductance of the toroid is n times mu naught ni over 2 pi r. Okay, and then times a divided by I. So I shows up in the numerator and the denominator. So just like we said earlier, as current increases, there shouldn't be any change in the inductance. The inductance should only be a function of the geometry of the inductor, and that's indeed the case. No amount of current affects the inductance. So let's simplify a little bit. The inductance of the toroid, let's see, there's an n and another n, so we'll call it n squared. So it looks like it's mu naught n squared a divided by 2 pi r. Well, that's pretty much the same thing as we had for the solenoid. We'll call that L subscript s, inductance of a solenoid. Mu naught n squared a over L. Here we have mu naught n squared a over 2 pi r. Okay, so now we have two equations for inductance. Inductance of a solenoid and inductance of a toroid. By the way, if you ever open up a computer or any electronic device that has a motherboard on it, you might find a donut-shaped coil of copper wire, and that's in the circuit to provide some amount of defined inductance. So in our next video lesson, we'll see how can adding inductors in a circuit help control the flow of current in a circuit.